Hi and Assalamualaikum. My name is Muhammad Rashid bin Rasul. I'm from Group 4, Section 1 for Project Presentation Control System Aircraft Pitch System Control. So, this is my team member, Ahmad Khairul, me, Muhammad Rashid, Muhammad Faris, and Nick Hamizan. So, for my part is introduction. Specific requirements have been established in effort to create efficiency control for a pitch angle system in order to ensure a peak performance. The reaction from the controller must have overshoot less than 10%, a rising time less than 2 seconds, and settle in less than 10 seconds for the settling time. And keep the steady-state error below than 2%. The design goal is further refined by a practice pitch angle requirement, which need increase from 0.02 radian to 0.18 radian in 2 seconds. 2% steady-state value and stabilization range of 0.196 to 0.2 or for radian in order to create feedback control that effectively manage pitch angle dynamic in response to step change. Control parameter will be adjusted based on the upcoming analysis for the open loop system transient response. So we control of this system using PID, and PID controller. PID controller. Yeah, that's all from me. Thank you and Assalamualaikum.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faris bin Aliki. Today I want to present about the method of this project, which is begin to simplify the modeling equations by plugging in some numerical values before determining the transfer function and state space models. First is transfer function. As you can see in the slide, PS, and second design requirements. First is overshoot less than 10%, second lifetime less than 2 seconds, and third settling time less than 10 seconds, and the steady state error less than 2 seconds, 2%. For the third open loop response, which is using the MATLAB command step after adjusting the input to the represent an elevator angle input of 0.2 radians, which is 11 degrees, and a system's stability can be ascertained by looking at the transfer functions poles. Next is closed loop response, which is include a feedback controller in order to maintain this system and ultimately fulfill our specified design requirements. The MATLAB command feedback can be used to produce the closed loop transfer function for the above controller CS simply to set equal to 1. And the closed loop transfer functions poles and zeros can be seen below by using the MATLAB commands pole and zero. The output Ys in the Laplace domain is computed as follows, assuming the closed-loop transfer function of the form Ys per Rs, where Rs is a step of magnitude 0.2. The plot displayed below, which matches the plot produced by the step command above within a round off, can be built by entering the following code in MATLAB command window, which is at the slide. For the next method, which is proportional control, to accomplish the required system behavior, apply derivative, integral, and proportional control combinations in the unity feedback architecture. And then run control system designer ppitch at the command line to launch the control system designer, which is used for design. The root locus plot, open loop would plot and closed loop step response plot for the given plant transfer function if controller CS equal to 1. And scale a unit step input to the system by setting the precomm pin center block Fs equal to 0.2 since our reference is a step function of 0.2 radians. Next is PI control. The drop of steady state Error is the frequently helped by integrate control. Error in this steady state is already satisfied. Still design a PI controller for the illustration purpose. Everything else will remain the same, and then the controller that appears after clicking the computer update is as follows. Next is PID control method, which is increasing a PID controller's derivative gain KD can frequently add in lowering overshoot. And then consequently, by including derivative control, it is possible to sufficiently reduce response oscillation, which is which in turn allows for an increased other gain and reduction in settling time. To verify the query, switch the controller type back to PID and press the update compensator button again. The resulting closed statement is shown at the result section. And next is simulating modeling method, which is using the state feedback controller designed to simulate the linearized aircraft model and building the state space model, make a simulating model using the formula. And possibility is to construct a state feedback plan model. Utilize the state space block found in Simulink to simulate an open loop system. Firstly, open a new model window in Simulink. From the Simulink source library, insert a step block. Double-click the step block and change the step time to 0 in order to supply an adequate step input at t equal to 0. Additionally, set the final value to 0.2 to indicate its assumed 0.2 radian reference. Open a new model window in Simulink. From the Simulink source library, insert a step block. And then to enter system settings, as displayed in the figure below, double-click on the state space block, and lastly the finished model at figure can be interpreted at the result.
Assalamualaikum. My name is Niam Zakim bin Hassan. Today I would like to present about result and discussion. Open loop response. Obvious that the open loop response completely failed to meet the design requirement. The open loop response is actually unsteady by considering the pool of the transfer function of pool using MATLAB. It's possible to ascertain the stability of a system. This function shows that the open loop transfer function has two pools, which is one of the imaginary axis and the other two on the left half of the complete explain. A pool on the imaginary axis denotes neither an unbound curve nor a zero decay of the system free response. A system with a pool on the imaginary axis can grow unbound when given an input. Even if the input is bound, even though the free response will not expand unbound. Next, result and discussion for closed loop response. The plot seen in figure which mesh within a round off. The plot produced by the step command can be created by entering the following code in the MATLAB command window. This closed loop system failed to meet to the specific design specification. As the plot in figure, the following section of this instance goes through a number of controller design strategies that result in closed loop system that indeed deliver the intended system characteristic. On a session, for the rest time, setting time, and final value can be added to the plot from the right-click menu under characteristic when the M file is run from the command line. From the figure, the rest time is 1.79 seconds. Transient or setting time is 35.1 seconds, and the final value is zero point 0.2. By looking at the closed loop step response in figure, it can be seen that the system has stabilized one feedback was added. Okay, for PI control, based on a figure, a PI compensator with KI is 0.0263 and KB 1.13 is this transfer function revealed that while integral control was at which the value of peak amplitude is 0.21 and 4.83% overshoot. Peak time is a measurement of how long it takes a system to operate at maximum capacity. A quicker response is indicated by a shorter peak time, which is preferable. Overshoot represent the extent by which the system response exceed the desired output. The oscillation was not reduced, but the average error in the signal was reduced more quickly, especially the error change sign after around 20 seconds. PID control. Based on figure, overshoot is the first important access to consider when assessing the performance of the PID control. The result is an impressive 7.5%, while the required percentage was set at 10%. Precision in flight control is largely dependent on rest time, a critical metric that measures system response. The PID control response to change in pitch order quickly with a rest time of 0.413 seconds. The settling time of 9.25 seconds that was attained is well inside the 10 seconds that was required this outcome. This outcome illustrates how well the PID controller can balance speed and stability to make sure the aircraft efficiently reach a constant pitch condition. For the error in steady state must be eliminated for pitch control to be precise. The PID control performed admirably in this instance, exceeding the strict criteria of less than 2% with a steady state error of 0%.
In summary, this assignment successfully achieved its primary objective of modeling a system in MATLAB, testing the open-loop system, and also designing a PPI and PID controller for a closed-loop system. The application of the Ziegler-Nielsen method and PID tuner allow for a systematic exploration of controller tuning methodologies. The analysis of the open-loop system revealed its inherent instability, emphasizing the necessity for a robust control strategy. The implementation of a PID controller in the closed-loop system showcased significant improvement, meeting key design criteria such as overshoot, rise time, settling time, and also a steady-state error. The detailed exploration of each controller type provide a valuable insight into their respective strength and limitation. And in order to improve the experiment further, it is suggested investigating a different setting of PID controller parameter configuration as a means for adjusting better trade-off between overshoot and settling time. Also, the study of advanced control strategy or algorithma might provide information on further enhancement that go beyond what is possible with conventional PID control. On the other hand, this assignment revealed our technical skill in using MATLAB software, and also on the other side, it illustrated how important control system design for practical application of real world. This study opened a broad view by demonstrating the successful application of control strategy in aircraft pitch control and advanced safety, stability, and agility aviation system. That's all. Thank you.